Let us continue with the problem what we have started solving in the previous lecture. The problem says that if the current density or the I core, that is the current density for corrosion of iron is 1.69 into 10 to the power minus 4 ampere per centimeter. Now, this is in case of iron. We know a few data. One is atomic weight of iron is 55.85 and density of iron is 7.86 gram per centimeter cube. Now, in case of MPY, the unit says that it is milli-inch per year. So, now we have to use the formula I into atomic weight of iron divided, it is to be divided by N F. In this case, the corrosion is taking place in this mode. So, N is 2. So, let me replace N with 2. F is 1 Faraday, and then we have to divide this term with density rho of iron. Then we will get the unit length by time. And now, all those things, let us put all those values of E, atomic weight, density of iron and the current density, and then convert it into MPY unit. Now, 1.69 into 10 to the power minus 4 ampere centimeter square, then this is 5.85 gram divided, it is to be 2 into 96500 into 7.86 gram per centimeter cube. So, this is we have to convert into MPY, which is nothing but milli-inch per year. So, we have to convert all the things into milli-inch term as well as the time part. Here the time is hidden in this section, because current is nothing but the rate of charge flow. So, this we can write that 1.69 into 10 to the power minus 4 coulomb per centimeter square per second into 55.85 gram 2 into, now this 96500 coulomb is basically the gram equivalent, which is nothing but the charge required to have a corrosion of 1 gram equivalent. So, 96500 coulomb into 7.86 gram per centimeter cube. Now, this two term cancelled. Now, this centimeter, now you will see that this one and this thing are getting cancelled, and gram both are getting cancelled. Now, this is, I am putting it in bracket. Now, second you convert into year. 1 second would be equal to 1 divided by 24 into 365 days, in 1 day 24 hours into 60 seconds, 60 minutes into 60 seconds. So, this is the year. So, 1 second would be this much here. So, now if you put all the things and then centimeter also you have to convert it into milli-inch. So, 1 centimeter equal to 1 by 2.54 inch. So, if you would like to convert it into milli-inch, so 10 to the power minus 10 to the power 3 milli-inch. So, now you put all the things in this, then you would get, let me put all the values and then you will see that the unit what is coming out after isolation is nothing but the milli-inch per year. So, 1.69 into 10 to the power minus 4 into 55.85 into 10 to the power 3 into 24 into 365 into 60 into 60. It is to be divided by 2 into 96500 into 7.86 into 2.54. Then you will see that this is coming out to be 77.251 milli-inch per year, which is nothing but MPY. So, now if you know the current density, the rate at which, since we know the current density is nothing but the rate at which corrosion is happening, so then you can convert it into MPY unit and also MDD unit according to your choice. So, now this is basically from the current density to MPY. Now, let me put one more problem, let me solve one more problem, that is the corrosion rate of an alloy. So, this is for pure metal, it is very easy. You have to take the atomic weight of the pure metal and then accordingly you can calculate what is the corrosion rate. Now, in case of alloy, you have to take, we have already seen that in case of alloy, you have to take equivalent, gram equivalent for the alloy. How to calculate gram equivalent for the alloy? Let us say if it is A, X, B, Y, C, Z, this is my alloy, where A, B, C's are 3 different elements and X, Y, Z they are in weight percentage and X plus Y plus Z equal to nothing but 100 in case of weight percentage and A, B, C's are elements. If you would like to find out what would be my equivalent, which is nothing but this formula you have to use, A n, A is basically the, in case of pure metal, A is the atomic weight, but since we are considering an alloy, so you have to find out the equivalent which is can be determined from this formula. If I, let me put, since I you have considered for current density, so let me put J in order to have a different notations, F J into M J divided by N J. Now, J is nothing but jth element. Let us say if I consider A to be the element, then A would be first element, B would be the second element, Z, C would be the third element. So, J value in this case would be 3. So, 3 elements, for example 1, 2, 3, it will take 3 values 1, 2, 3. Now, if you, this is equivalent, this is gram equivalent for the alloy. Now, if J is nothing but the fraction of that particular jth element. Let us say if you consider A element, the fraction would be X. If you consider B element, fraction would be Y, and accordingly for C, fraction would be Z. And Nj is the, let us say A is coming out by forming ions, then you have to see what is the reaction there. The A can come out like A N plus Ne. So, then that case N j is for A element is N. Now, if N value comes out to be 2, then this would be 2. So, in case of A element N would be 2. Now, for this element like that, so you can find out what is my equivalent. Now, again let us say you would like to find out what is the expression of corrosion rate in the form of MPy. That case you need to know what is my density. Now, again you can also find out density by doing experiment, but one way to find out density is again you can use another formula, density of alloy, which you can take it as Fj into rho j. So, here Fj is the fraction of the element you are considering and rho j is the density of that jth element. Now, like that you can find out rho of that alloy. Since you have to use the formula, here it is written. So, in that case this A Fe it will be converted into A by N equivalent. Now, here the in case of iron the equivalent is A by 2, A Fe by 2, but in case of alloy it would be A by N. So, you do not have to put the N value separately. Now, let me talk out one such problem. Let us say AI Si 316 alloy. This alloy, now I know what are the fractions of different elements. Chromium is 18% and all are in weight percentage. This is weight percent. 18%, nickel is 8%, molybdenum 3% and Fe 70%. So, now you are seeing that, let me calculate 18 plus 8, 22, 26 plus 3. So, you can, and 1% could be some impurity elements, but that will not be very crucial for the overall calculation. Let me see that this is my overall composition. So, you can also put it as 71%, no problem with that. But let me go ahead with this, because now I can find out what is my N for different elements if it goes in the solution. So, N, let us assume that the N is in this case 1. N means the way the element is going into the solution in the form of ion. Let us say chromium, then it go as +1 plus 1e, like that it would move. Nickel, N is 2, molybdenum, N is 1, iron, N is 2. If I assume those values, then I can also, I know also the density of different elements. This is 7.1 gram per centimeter cube. This is 8.9 gram per centimeter cube. This is 10.2 gram per centimeter cube, and this is 7.86 gram per centimeter cube. Also, you know what are the atomic weight, atomic mass of these elements. This is, let us say, A element. So, here it is 52.01 gram per mole. Now, this is 58.68 gram, 95.95, and this is 55.85. Now, with this data set, I can also find out what is my gram equivalent. Now, A n would be equal to then 0. The formula we would be using, that is A phi j A j by N j. A j is basically the atomic weight of that element, jth element. So, 0.18 for chromium, it is 0.18 into 52.01 into by 1 plus 0.08 into 58.68, because this is percentage. So, you have to divide with 100, and then this is 2 plus 0.03 into 95.95 divided by 1 plus 0.7 into 55.85 by 2. Now, this I can find out what is my value. This is 34.135 gram. Now, for this, if I know that the corrosion rate in the current density term, if it is given as 1 microampere per centimeter square, so this is my I core. So, in this alloy I know the I core, so I have to find out in the form of MPy. So, that case I know this. I can also find out what is my rho. Let me note down this A value, A by N equivalent equal to 34.135 gram. Now, similar way I can find out what is my rho of the alloy. So, this is 0.18 into the rho of chromium 7.01, like that, 0.08 into 8.9 plus 0.03 into 10.2 plus 0.7 into 7.86. So, now from that you can find out my rho of that alloy would be 7.7818. So, let me put 2 up to 3 decimal, let me take gram per centimeter cube. So, I can also note down what is my rho of that alloy is nothing but 7.782 gram per centimeter cube. Now, we know that in case of pure metal, this is my formula to convert to have corrosion rate expression in the form of length by time. Now, in this case I have taken AFE. Now, if you take this ratio is nothing but the gram equivalent. Now, in this case, in case of, so the modified equation for the alloy would be I into A by N equivalent divided by F, which is Faraday, into rho, in this case rho of the alloy, you have to take rho alloy. So, now you have to put now all the values and do the same treatment the way the treatment has been done for the conversion of units. You would get that this value is coming out to be 0.56 MPy. And you have to put this 1 microampere per centimeter square, that means 10 to the power minus 6 ampere per centimeter square, and you put this value, you put this value in this case, and for rho alloy this one the value, this is the value at 1 Faraday is 96500 coulomb per gram equivalent. So, you would get this is the corrosion rate expression in the form of MPy. If you would like to do in the form of MTD, that case you do not have to use rho alloy, because if you divide this thing with the rho, then it would come the length, the unit would come in terms of length penetrated, penetration depth per unit time, but if you do not use this, then it would be mass lost per unit time per unit area. So, that you can also convert into MDD, which is milligram per day per decimeter square. So, this is about the rate expression for corrosion. Now, let us keep continuing with kinetics of corrosion. Now, we know the concept of single electrode potential, and not that too in the reversible condition and in the standard state E0 m plus n m. This is standard reduction potential. And what does it mean? It means that if you have one unit, if your concentration is 1 unit activity or unit activity, and temperature is 25 degrees Celsius, pressure is 1 atmosphere pressure, that time if you measure the reduction potential, then this value is coming, the value which will come out, that would be termed as E0, which is standard reduction potential for that particular metal or for the particular element. Now, what does it mean? It means that m n plus n e going to m. Now, there is equilibrium, there is an equilibrium between m n plus ion and m. Now, if you see the metal surface, this is my metal surface. Now, when the metal surface, it forms metal ion, so it leaves metal ion n plus. So, like that you can have m n plus m n plus m n plus. So, you can have over the entire exposed surface, you can have a section where you have m n plus ion layer, and on the other side it is metal surface. Now, you have two sections, one is metal section, one is ion section, positive ion section, and there is an equilibrium. That means, the metal ion that is forming from the metal surface, the rate at which it is forming, or you can say the flux of metal atom that is coming out from the metal surface and forming metal ion n plus ion, the rate at which that is forming, that means the flux, which is nothing but, let us say, mole per centimeter square per second. That means the flux, which is the number of moles per unit area per unit second. So, that flux, the way it is forming this side, and the similar way the metal ion also is getting reduced and forming metal. So, flux at which this is going into this and this is going into m plus n plus ion, those two fluxes are same. So, that suggests that the system is at equilibrium, and that too it is happening at particular temperature and pressure. Now, when you have this, let us say I am considering only this part. This part means a sort of deposition, metal ion is depositing on the metal surface again. Now, if you consider this section, then metal is coming out and forming metal ion. Now, we know what is the corrosion rate expression. The metal ion formation is nothing but the corrosion, and also we know that corrosion is, if you would like to find out what is my rate of corrosion or the rate of formation of metal ion formation, that is nothing but the current density, which is current density. Now, once you know the current density, you know that what is my rate of reaction. And again, if you would like to find out the amount of metal ion that is forming per unit area per unit time, then also you can have conversion, which is nothing but I A of that metal, which is the atomic weight of that metal, divided by N F. And in this case, the number of electron that is participating in this reaction is N. Now, this is my rate of reaction. At the same time, when it is at equilibrium, so the rate at which this is forming and rate at which metal is forming. So, this is my rate, actual rate in terms of weight or mass loss per unit area per unit time if metal is forming metal ion. If metal ion is forming metal, which is nothing but the reduction process, that time the rate at which the metal ion is depositing, both are same at equilibrium. So, I can write in terms of current density, I can write that, let us say if I A, let me put it as A, which is small a, I subscript A, for A means nothing but anodic reaction. Anodic process means where oxidation occurs, and oxidation means metal is forming metal ion. So, same way I can term this rate I can term it as IA, which is nothing but the anodic process or the oxidation process. Similar way I can give another terminology for the reduction process, which is nothing but the cathodic reaction. So, I can term it as, if I would like to find out what is the rate of cathodic reaction, I can term it as IC, which is C is nothing but small c, I subscript small c, cathodic process. Cathodic process. Now, if you would like to find out what is my rate of anodic process, IA, A of metal, which is atomic weight of metal, NF, and I can find out this is anodic rate and cathodic rate is IC into A of M divided by NF. So, if these two rates are different, so definitely these two terms would be different, but at equilibrium I can have the same rate of this reaction, forward reaction as well as backward reaction. So, that case I will have a relation between these two, which is nothing but equal. This is at equilibrium. Now, if you consider the standard reduction potential, that case you do not have any corrosion, because you have already maintained one unit activity to be 1, the metal ion concentration in the solution. So, you have equilibrium between those many atoms, those many ions in the solution with the metal surface. So, it is something like non-corroding system, because the rate at which metal ion is forming, the rate at the same rate metal ion is also getting deposited. So, it is a kind of non-corroding system and a reversible system. So, that case I see that this value both are same, this value both are same. So, this two are getting cancelled at equilibrium. So, IA equal to IC. Now, if you have this, I can term it as I0, provided the system is at non-corroding system and reversible condition. So, that time I term it as I0, which is IA equal to IC equal to I0, and then this I0 is considered to be exchange current density. This is considered to be exchange current density. Now, we see this relation. Now, there is one thing that is inherent into it, but we have to make it clear what is the inherent part. If you see the direction of IA and IC, these two directions are opposite in nature. For example, IA is this direction, IC is this direction. So, they are opposite. though the values are same, if you take mod value, these two values are same, but if you do not take mod, then the magnitudes are same, but you have a sign difference. So, the convention is, it is the negative sign is considered in front, is written in front of IC in order to just indicate that IC is having opposite direction to the IA. So, actual expression would be IA equal to minus IC. This minus sign indicates the direction of the flow of the charge or the current, and I0 is nothing but exchange current density when IA equal to minus IC in the reversible non-corroding process. So, that time we term it as exchange current density, and this exchange current density has a huge implication on the corrosion process. So, exchange current density is one important kinetic parameter for corrosion process. Now, in order to see the implication of exchange current density, let me see one situation. Let us see you have same reaction N plus Ne M. Now, you can have a concentration cell where you have the same metal dipped in a solution of M plus ion, Mn plus ion, this is the same metal. Now, the same another cell you create where you dip the same metals into another solution where the metal ion Mn plus you are maintaining, and now here the concentration is C1 and here the concentration is C2, and C1 not equal to C2. See, if you connect it with a salt bridge and then connect with the external wire, then you will see the current is flowing. You have connected these two metal rods, same metal rods, those are dipped in two different solutions, same solution with a different concentration of N plus ion, and you have made the circuit complete. You will see the current is flowing, and this current will flow if C2 greater than C1, you will see that current is flowing from this end to this end. If you have more C2 more than C1, you will see that reduction potential at this electrode is more than reduction potential at this electrode. So, current will flow from higher potential to a lower potential. Now, let us say these two areas which is exposed to the solution, those are different. Now, the external source, external circuit, the current is I. Now, here the exposed surface is A1, here A2, and here the exposed surface is A1. Now, the same current is flowing through those two electrodes, but the exposed area to the surface, to the solution are different for those two metal surfaces. Now, what would be my current, anodic current and cathodic current? You can, if you are considering this to be anodic current, the opposite you can consider as a cathodic current. So, IA equal to IC, but if you would like to find out what is my current density, then IA divided by the anodic area is this one A1, and IA IC divided by A2. Now, I know that the same current is flowing through those two electrodes, but if you would like to find out what is my current density, this is my current density on the anodic surface, this is my current density on the cathodic surface. I can write it as IA, small ia, which is current density, this is small ic with a notation with a negative sign. Now, do you think that these two are equal? Because these two are definitely unequal. Now, if these are not equal, So, though the same current is flowing, but you will see that the rate at which cathodic reaction is taking place is entirely different than the rate at which anodic process is taking place, and that is happening just because of different area, exposed area on the two metal surfaces. So, here it is very important, you will come to know later that if you couple copper and iron, then you will see that let us say you have a copper plate, two copper plate, you have riveted this two copper plate with the iron section, iron rivet, then you will experience the effect of this IA and IC on this particular structure. So, we were discussing about this iron rivet. You are using if iron rivet is used to fasten two copper plates, and that is in the seawater system. Now, this situation would be very crucial. The current density would be very crucial, not the current value. If you see here, the current in the circuit, it will be a closed circuit. So, current in the circuit would be same. The current what is flowing through iron rivet and the flowing through the copper rivet, both are same. But since now the amount of cathodic reaction, if you consider, that reaction is taking place over the entire copper plate, and in this case copper, this is copper plate. The copper plate is acting as the cathodic surface, and the cathodic reaction will always happen on the cathodic surface. So, here the cathodic reaction is taking place, and of course, if it is in seawater, the cathodic reaction would be oxygen reduction. So, in this case cathodic reaction would be O2 plus 2H2O plus 4E going to 4OH minus. So, this is a cathodic reaction in case of neutral solution, since seawater is a neutral solution. So, cathodic reaction is taking place over the entire cathodic area, and accordingly, if this reaction is happening over the entire cathode surface, and if you compare the area ratio of cathodic section and anodic section, here the iron is acting as the anodic area, and the anodic reaction is definitely iron plus iron going to Fe plus 2E. This reaction is taking place on the ionic surface, and if you compare the galvanic series, I will come to that galvanic series later on. So, this copper and iron, if you couple them galvanically, then you will see that copper is acting as a cathode and iron is acting as anode, and once iron is acting as anode, so anodic reaction will take place on the iron surface. Now, here two things. One is you have huge surface area for cathodic reaction. So, now you have huge amount of electrons that would be needed for this cathodic reaction. So, where from these electrons will come? These electrons will come from these anodic reactions. So, you have to have a larger amount of electron production in order to have a charge balance, because cathodic reaction is taking place this one, and that is taking place over the entire surface, and the amount of charge that is required would be greatly increased since the cathodic area is more. Now, the current, if you consider the current that is flowing through the system is I. Now, what would be my IC? So, IC would be IC minus AC, which is the cathodic area, which is nothing but the copper. Let me put copper. And now, if you consider the anodic area, which is nothing but IA by AA. IA is basically the anodic current, which is same as the current that is flowing in the circuit. Now, this IA is a very small quantity, because it is a rivet, the small section which is exposed. Now, what would be my then IA? This is my IA, which is nothing but the current density for the anodic reaction, and here it is IC minus IC. Now, what would be the values if you compare the values, magnitude of this IA and IC? since there is this I copper, A copper is very, very large, that the area of the copper surface is very, very large, and this area is very, very small. So, this would be very, very large compared to IC if you compare the magnitude. So, what do you mean by IA? I is the rate at which anodic reaction is taking place. So, this reaction is taking place. So, if IA is small IA is very, very large compared to the current density on the cathodic surface, then the corrosion rate of iron would be enhanced to a great extent. So, now you understand what is the importance of current density. Now, we have started with exchange current density. Now, before going into the next section, the how to express the exchange current density with respect to the activation energy for metal ion formation. So, before that, let me see what are the factors that can affect I0. The factors are electrode material, let us say for the same reaction, hydrogen evolution reaction H plus. For this reaction, if you would like to consider what would be the value on platinum surface or on zinc surface, you will see that the I0 value of this reaction. So, we write it like this: I0 H plus H2, this I0 of this reaction on platinum surface. So, I am writing in the bracket the metal surface, it means on that surface this reaction is happening. So, on the platinum surface would be equal to, generally this value in case of acidic media, it value goes to around 10 to the power minus 2 to 10 to the power minus 3 ampere per centimeter square. Same reaction. Now, if this reaction is considered in case of zinc surface, then this value goes to 10 to the power minus 10 to 10 to the power minus 11 ampere per centimeter square. So, you see same reaction, you just change the electrode material, you are having huge difference in the current density or the exchange current density. Now, what does it mean? If you have a very, very high exchange current density, because we consider that on the platinum surface I0 for hydrogen evolution is very, very large, that means that the quickness of attaining a reversible condition. Quickness in attaining the reversible condition, because I0 is nothing but the rate of evolution, hydrogen evolution or hydrogen ion formation in reversible condition, and if you have a very, very large value, that means that the equilibrium is attaining at a very, very fast rate. Or the advantage of having platinum, it means that let us say you disturb this equilibrium. If you disturb this equilibrium by some means, then if it is a platinum electrode, then the equilibrium again will be attained quickly. So, that would be very much helpful. You will see later on what is the effect of these different I0 values. So, this is the effect of electrode material. Same way you can have difference in I0 value of the same reaction if you are using acidic media or basic media. So, second case, I am just noting all the conditions or the factors that would affect I0 values for a particular reaction. Then surface condition, you know that we can have a platinum electrode or platinized platinum electrode. Now, if you compare these two surfaces, the platinized platinum electrode, the exchange current density of hydrogen evolution is much more than that on platinum surface. So, these two surfaces, if you consider platinum and platinized platinum electrode, these two surface conditions are different. On the platinum electrode, platinized platinum electrode, you have the platinum particles which are deposited on the platinum surface. So, you have a much more actual surface areas, and that actual surface area will actually affect the exchange current density for this reaction. Now, third is the solution. You will see that if you are considering acidic media, if you are considering basic media, this for the same reaction the exchange current density would be different. Then fourth is environmental condition. Let us say you are considering, in case you are considering a dry, you are considering an area where you have much more presence of salt in the atmosphere, or in the area where you do not have much presence of salt in the atmosphere. Let us say you are considering one section, let us say you are doing some test in Visakhapatnam, Vizag, or you are doing some test which is a which is the sea region, and if you are doing some test in the Ladakh region, you will have a difference in I0 values. Then 5, temperature. Definitely temperature will definitely affect the I0, because the reaction rate, it considered I0 is nothing but the reaction rate, or exchange current density is nothing but the reaction rate in the reversible condition. So, the rate of the reaction always will be affected by the temperature. Then you have surface roughness. So, surface roughness, actually this relates to this. Okay. So, it is nothing but the same thing. So, let me remove this. So, these are the factors which can affect the exchange current density. There are other factors, and these are the main factors. Now, let me now consider how to have a relation between I0 and the activation energy for ion formation. Now, when you are considering this process, it's not happening like that way, that metal is immediately forming metal ion from metal ion, or metal is immediately forming metal. In fact, these metal ion and metal, when they are crossing from metal to metal ion or metal ion to metal, they are crossing an energy barrier. Now, if you consider this is my metal surface and this is my ion surface, N plus and M. Now, it is not happening like this, simply it is not going like this, or simply it is not coming back like this. If you would like to find out what is the energy situation at these two sections, then you will see that if you consider this is my free energy or G axis, and if it is my reaction coordinate RC, or it is basically nothing but the distance. This is the distance, and when it is at equilibrium, that case these two sections are at low energy level, and those will remain in the energy well, and there would be an energy barrier which is nothing but del G star. I am putting it as del G star because this is nothing but the difference. This is, let us say, G1, this is G2. So, this is the difference, difference is nothing but the del G star. I am just putting as del G star. So, now for this case, and mind it, this is, there is an existence of equilibrium. In that case, I can find out what would be my flux from this section to this section, and flux of metal ion to this metal surface, because that equilibrium is existing. So, rate at which, let us say if it is rate 1 and this is rate 2. So, rate at which metal ion is forming and the rate at which metal ion is depositing on the metal surface, both are same. So, that rate can be expressed in the form of flux. The flux of metal I can put it as mole per centimeter square per second. I can express this in the form of this equation N1 nu 1 F1 exponential minus del G star by RT. Flux of metal going to form metal ion. What is N1? N1 is moles per unit area in a favorable position, that this N1 is the number of moles per unit area on this surface which are in a favorable condition to go from this to this. We are not sure that whether N1 entire N1 will go to the other side or not. That would be decided by F1. F1 is the fraction of atom or fraction of moles actually going from this to this. And what is my nu 1? Nu 1 is the frequency at which, the mean frequency at which the metal atoms are vibrating. So, this is around 10 to the power 13 per second. So, this is my flux from this to this. I can also write the flux of metal N plus which is going to this. So, I can write that as, let me remove this part. I can write the flux of metal ion, again it is in moles per centimeter square per second. It can be written as N2 nu 2 F2 exponential minus del G star by RT. And since there is an activation barrier and this is a thermally activated process, I can express in the form of the flux, I can express in the form of Arrhenius equation. Now, you see that at equilibrium, the flux of metal ion that is going to metal, this should be equal to this, because this is nothing but the rate, this is nothing but the rate, and we know that at equilibrium R1 equal to R2, and I can put it as this one is R1 and this is R2. So, R1 equal to R2, and we know that this del G star, in both the cases these terms are coming, the exponential term both will get cancelled. If you have this equation, then you will see that N1 equal to N1 nu 1 F1 equal to N2 nu 2 F2. Now, this N2 is basically the number of moles per unit area on this section. So, we have an important relation that this is both are equal. Now, generally this N1 nu 1 and F1 is considered to be 1. If you think that all the metal what is coming on this surface that are getting accommodated on this section, and the same way the number of metal ion which is going to this metal surface because of reduction process are getting accommodated on this surface. So, if A1 equal to F2, it could be 1, and N1 and N2, since these are at equilibrium, so this would also not vary, and nu 1 generally both the cases it is close to 10 to the power 13 per second. So, if this term I can write in the form of a constant. Let me stop here.